I made a terrible mistake. In 1916, when I published my equations describing spacetime, I never imagined they would predict something so monstrous that it would haunt me forever. It was winter in Berlin. The war raged across Europe, and I sat in my small office, wrestling with mathematics that seemed to describe reality itself. The equations were beautiful, elegant curves describing how mass bends the fabric of space and time. I thought I had found the secret of gravity, the hidden mechanism that keeps planets in orbit and makes apples fall. I was wrong. I had found something far more sinister. My colleague Karl Schwarzschild, brilliant mathematician fighting on the Russian front, took my equations and found a solution that made my blood run cold. While dodging bullets and artillery shells, while watching his fellow soldiers die in the frozen mud, he was solving my equations, and what he found changed everything. He discovered that space and time could curve so severely that nothing could escape. Not matter, not energy, not even light itself. Dr. Schwarzschild in his tent, candlelight flickering on pages covered with calculations, the sound of distant gunfire echoing through the night. He was dying of an autoimmune disease contracted in the trenches, his body failing even as his mind worked feverishly on the mathematics of curved spacetime. In his final weeks, he discovered mathematical monsters hiding in my equations. Schwarzschild died just months later, killed by disease on the battlefield. His body was buried in the frozen earth of Russia, but his mathematical ghost lived on, describing objects so dense they would tear holes in reality itself. We call them black holes now. Though I preferred dark stars, it seemed less apocalyptic, less like the cosmic nightmares they actually are. When his solution reached me in Berlin, I stared at the mathematics for hours. The equations were correct. I could see that immediately. But what they described seemed impossible, even obscene. A region of space where the curvature became so extreme that geometry itself broke down. I spent sleepless nights walking through the streets of Berlin, trying to convince myself that nature would never allow such things to exist. There must be some mechanism, some unknown physics, that would prevent matter from collapsing to such extremes. The universe couldn't be that cruel, that strange. I was wrong again. You think you understand what nothing can escape means, like a deep well. Throw something too weakly, it falls back down. But that's not what happens near a black hole. That's not even close to the horror my equations reveal. Let me tell you what really happens when light meets its match. Picture this. You're holding a flashlight on Earth. Point it up, press the button. Light shoots out at 299,792,458 meters per second, the cosmic speed limit. I discovered this speed is fundamental to the universe itself, woven into the very structure of space-time. The photons race away from Earth, climbing out of our gravitational well, gradually slowing but never stopping. They escape. They reach the stars. But here's something I learned that still gives me chills. That speed of light isn't just fast. It's the maximum speed at which cause and effect can propagate through the universe. It's the speed at which now spreads from one place to another. When I realized this, I understood that light doesn't just happen to travel at this speed. Light is this speed made manifest. Now imagine standing near a black hole. Same flashlight, same button. But when you press it, something that violates every intuition about reality happens. The light shoots out at exactly the same speed it must. That's the law. The speed of light is absolute, unchanging, the same for all observers. But as those photons climb away from the black hole, fighting against curved space-time, something impossible occurs. They don't just slow down, they stop, they hover, they fall back. Light itself, the fastest thing in the universe, the very thing that defines reality's speed limit, cannot escape. It gets pulled back like a thrown stone. Except stones were never supposed to be the fastest thing possible. When I first understood this, I walked to my window and stared at the streetlights outside. Each photon streaming from those lamps was traveling at the ultimate cosmic speed limit. Yet my equations said there were places in the universe where even this ultimate speed wasn't fast enough. The implications made my hands shake. This broke every intuition I had about the universe. How can something traveling at the ultimate speed limit still not be fast enough? The answer lies in what I discovered about gravity's true nature, and it's stranger than any fiction. I had to abandon everything Newton taught us. Gravity isn't a force pulling things together. That's Newton's old picture, and it's beautifully wrong. Gravity is space-time curvature itself. Massive objects don't pull. They warp the very geometry of space and time, creating valleys and hills in reality's fabric. Think about this carefully. Space and time, the stage on which all physics plays out, are not fixed. They're dynamic, flexible, responsive to matter and energy. When I first published this idea, other physicists thought I had lost my mind. Space and time bend? Impossible. But the mathematics demanded it, and later experiments confirmed it. When you drop a ball, it's not being pulled down. It's following the straightest possible path through curved space-time. The ball thinks it's traveling straight, but that line curves through warped geometry, so the ball falls. The ball is doing nothing but moving through curved space, and we interpret this motion as falling. Now imagine taking our sun's mass, 2 times 10 kilograms, a number so large it's meaningless to human intuition, and compressing it to a sphere just 3 kilometers across. The density becomes unimaginable. 5 times 10 mule and per cubic meter. At this density, a teaspoon of matter would weigh as much as Mount Everest. The curvature this creates is so extreme that space-time doesn't just bend, it folds in on itself like paper creased beyond repair. It creates what we call an event horizon, a boundary from which no event can ever be observed by the outside universe. Cross that boundary, and you're not just trapped, you've entered a region where all paths through space-time lead inward. Every direction you could move, every path you could take, curves toward the center. Up becomes down, forward becomes inward, left becomes inward, left becomes inward. The geometry of space itself has been so violently distorted that escape becomes geometrically impossible. It's not that there's a force preventing escape, it's that the very meaning of a way has been destroyed. But here's what truly terrified me when I first understood this. From your perspective, falling past the event horizon, nothing seems different. You don't feel crossing some cosmic point of no return. Time flows normally. Space looks normal. You're just falling through emptiness, accelerating toward the center. This haunted me for years. I would lie awake in Princeton, staring at the ceiling, trying to reconcile this paradox. How can crossing the most significant boundary in the universe feel like nothing? How can the moment when you become forever isolated from the rest of reality be completely ordinary from your perspective? The answer reveals something profound about the nature of time itself. Time is not universal. It's not absolute. It's relative, flexible, dependent on gravity and motion. Near a black hole, time itself becomes twisted, stretched, distorted beyond recognition. It's only when you look back that you see the horror. The light you emit, trying to escape, becomes redder and redder as it climbs out of the gravitational well. This is gravitational redshift, the stretching of light waves as they climb out of curved space-time. To someone watching from far away, you appear to slow down, redden, and fade, frozen forever at the event horizon. But you never stop falling inward. I remember the first time I worked through this calculation. I was in my study in Berlin, equations covering every surface. As the mathematics unfolded, I realized we were describing something impossible. Two equally valid perspectives on the same event that gave completely contradictory results. From outside the black hole, you never cross the event horizon. You slow down asymptotically, your clock ticking slower and slower relative to distant observers, your light getting redder and redder until you fade from view. From the outside universe's perspective, You're stuck there forever, frozen in time like an insect trapped in amber. From your perspective, you fall right through the event horizon in seconds. Your watch ticks normally. You see the universe above you blue shift and speed up. You witness the entire future history of the cosmos compressed into moments as you fall toward the singularity. Both views are correct. Both are real. The black hole has broken our understanding of simultaneity, of cause and effect, of what it means for something to happen. This paradox still haunts physicists today, nearly a century after I first stumbled upon it. And what happens inside? My equations predict something even more disturbing. The tidal forces, the difference in gravitational pull between your head and feet, become infinite at the center. Infinite. Let me explain what this means. Even here on Earth, you experience tiny tidal forces. Your feet are slightly closer to Earth's center than your head, so they feel slightly stronger gravity. The difference is negligible, less than 1/1,000,000%. You never notice it. But near a black hole, this effect becomes monstrous. If you're falling feet first toward a black hole with the mass of our sun, by the time you reach the event horizon, the gravitational force on your feet will be noticeably stronger than the force on your head. As you continue falling, this difference grows exponentially. You get stretched. First gently, like taffy being pulled, then violently. Your body elongates, your atoms are pulled apart, your molecular bonds snap, one by one. We have a term for this process: spaghettification. The clinical terminology masks the horror of what actually happens. At the singularity, if such a point truly exists, the tidal forces become infinite. Your atoms are crushed into a point of zero volume and infinite density. The very concepts of size, shape, and structure become meaningless. We call this a singularity, a point where physics breaks down completely, where our equations produce nonsense answers like infinity divided by zero. It's not just that we don't know what happens there, it's that the questions themselves become meaningless. What does what happens mean when time and space have been crushed out of existence? But perhaps most disturbing, black holes aren't rare curiosities locked away in some distant corner of the universe. They're common. They're inevitable. They're the natural endpoint of stellar evolution for any star massive enough to ignore the forces that keep normal matter stable. Every star in the sky is fighting a war. Nuclear fusion in the core pushes outward with tremendous force, trying to blow the star apart. Gravity pulls inward with equal determination, trying to crush everything to a point. For most of a star's life, these forces balance. The star exists in a delicate equilibrium, burning hydrogen into helium, converting mass into energy according to my equation E(x)(a². But eventually the fuel runs out, the nuclear fire dies, and gravity wins. For smaller stars like our Sun, the collapse stops at a white dwarf, matter crushed to incredible density but still held up by electron degeneracy pressure. For larger stars, even this isn't enough. The collapse continues, crushing protons and electrons together to form neutrons, creating a neutron star, matter so dense that a teaspoon would weigh as much as Mount Everest. But for the largest stars, those more than about 25 times the mass of our Sun, even neutron degeneracy pressure isn't enough. Nothing in the known universe can stop the collapse. The star implodes in a catastrophic supernova, and what remains continues collapsing forever, crushing matter and energy and space-time itself into a geometric point of infinite density. The mathematics forced me to accept this. Every massive star that dies creates one. Our galaxy contains millions, possibly billions. We're living in a cosmic graveyard filled with the corpses of dead stars, each one a wound in space-time that can never heal. Right now, 26,000 light-years from where you sit, there's a supermassive black hole containing 4 million solar masses lurking at the Milky Way's center. We call it Sagittarius. A. It's been there for billions of years, slowly consuming gas clouds and unfortunate stars that wander too close, growing larger and more massive with each meal. I used to find comfort in the vastness of space, the idea that these monsters were so far away they could never affect us. But then I learned about gravitational waves, ripples in space-time itself, that travel at the speed of light. When two black holes collide and merge, they ring space-time like a bell, sending waves of geometric distortion across the universe. These waves have been passing through your body your entire life. The collision of black holes billions of years ago, billions of light years away, is still stretching and compressing the space between your atoms by amounts smaller than 1,000th the width of a proton. The universe is constantly vibrating with the death screams of matter falling into cosmic oblivion. We've seen it. Modern technology has advanced to the point where we can detect these gravitational waves, feel the universe shuddering as black holes devour each other. We've photographed event horizons themselves, capturing the shadow of nothingness against glowing gas spiraling to its doom. The first image of a black hole's event horizon was released in 2019, the supermassive black hole at the center of galaxy M87. When I saw that image, I felt a chill that had nothing to do with the temperature. There it was, the mathematical prediction I had wrestled with over a century ago, rendered in stark visual reality. My equations, written in a small office in Berlin while the world tore itself apart in war, predicted exactly what that image showed: a dark sphere surrounded by a bright ring of superheated matter, the last light that will ever escape from that region of space. The shadow of the event horizon, perfectly circular, exactly the size my equations demanded. It was beautiful. It was terrifying. It was the universe confirming that reality is stranger than any human mind was meant to contemplate. And still, after decades of observations and calculations, after seeing my wildest mathematical predictions confirmed by reality, I lie awake disturbed by what we've discovered. We live in a universe where matter can become so dense it punches holes in reality itself, where the fastest possible speed still isn't fast enough, where the laws of physics that govern everything else simply stop working. The mathematics is beautiful, elegant, precise. The predictions match observations perfectly, but the reality it describes is a cosmic nightmare. Regions where information goes to die, where future disconnects from past, where the universe develops amnesia. This troubles me more than I can express. Throughout my career I believed in the deep rationality of the universe. I famously said that God does not play dice with the universe, expressing my faith that underneath the apparent randomness of quantum mechanics lay some deeper deterministic order. But black holes force me to confront something worse than randomness. Regions of space where order itself breaks down, where the very notion of physical law becomes meaningless. At least dice follow probability theory. At least random events obey statistical rules. But at the singularity inside a black hole, even mathematics surrenders. Sometimes I wonder if Schwarzschild was fortunate to die before seeing what his solution truly meant. He found the mathematical description of cosmic monsters, ultimate prisons from which not even light escapes. And once you've seen such things are not only possible, but inevitable, you never look at the night sky the same way. I remember standing outside my house in Princeton on clear nights, gazing up at the stars. Each point of light represented a sun, possibly with planets, possibly with life. But my equations taught me a darker truth. Every light up there is either dead, destined to die, or orbiting something already dead that left behind wounds in space-time. The universe isn't the welcoming, comprehensible place I once thought. It's stranger and more terrifying than any human mind was meant to contemplate. We've discovered that reality itself can be destroyed, that there are places where the very concepts of space, time, and causality become meaningless. But we contemplate anyway. We point telescopes toward these cosmic graveyards and study them with fascination and dread, because understanding them, even if it disturbs our sleep, makes us human. We're the only species we know of that can look into the abyss and describe it mathematically. The black hole doesn't care about our understanding. It doesn't care about anything. It simply warps space-time with such brutality that light itself dies trying to escape. And somewhere in infinite darkness beyond the event horizon, information and energy that once belonged to stars, planets, perhaps living worlds, continues its final journey toward a point where physics surrenders to the incomprehensible. What happens to the information? This question haunts modern physicists. If you throw a book into a black hole, what happens to the information contained in that book? Does it disappear forever? But information can't be destroyed. That's a fundamental principle of physics. Yet black holes seem to violate this principle. They consume information and give nothing back. This is the information paradox, and it suggests that either our understanding of black holes is incomplete, or our understanding of information is wrong. Both possibilities are disturbing. After a century of physics, we're still discovering that reality is stranger than we imagined. That is what my equations revealed. That is the legacy of my attempt to understand gravity. Not just that massive objects spend space and time, but that they can bend them so completely they tear holes in reality itself. Places where the universe forgets itself, where the story of cause and effect breaks down, where even the fastest thing in existence cannot escape. And the most terrifying part? We're still learning how strange these monsters truly are. New discoveries emerge regularly. Hawking radiation, holographic principles, information paradoxes. Each insight reveals that black holes are even more bizarre than we thought. Sometimes I feel like I opened a door that should have remained closed, unleashed mathematical demons that reveal the universe to be far more dangerous than we imagined. But science doesn't allow us to unsee what we have seen. We must live with the knowledge that the cosmos contains regions where reality ends, where physics breaks down, where even light finally meets its match and dies. This is what my equations taught us. And it is both more beautiful and more terrifying than anything I ever imagined.